Okay, let's begin. Uh, Today we are going to look at quantum numbers. Okay, so I know that many of you are watching the channel now. Okay, I want everybody to subscribe. Okay, please subscribe and watch. Okay, thank you so much. Uh, Today we are going to look at quantum numbers. Okay, this quantum numbers is a very important topic, uh, particularly for AP chemistry. Okay, but also for honors chemistry. For general chemistry, it might be useful. It's better that you know that this concept for your chemistry classes. So, what are these quantum numbers? Quantum numbers, I am going to put a general video about how these quantum numbers came from Schrodinger's equation. Okay. So, but here we are going to look at only purely on what are the quantum numbers and what the quantum numbers come to tell you, why there is a need for quantum numbers, and how to calculate them. Okay. So, first, the electrons. We know that the electrons go around the nucleus, okay, but they go in certain orbits. And in each and every electron that they go around, so when in every orbit, the electrons that go around, there is a specific distance from the nucleus. So we can call them radius 1, radius 2, radius 3. Okay. So the radius differs. The electrons are uh, either close to them or farther to them, further to the nucleus. Okay. So this idea of how do we know that first of all this electron exists in orbits. Okay, that's most important thing. That came from ionization data. Okay, that we are going to look later on. Okay. First, let's understand what is quantum numbers. So define this orbital. Okay. We need three quantum numbers, and each and every electron will be defined by four quantum numbers. Okay. The first quantum number is called as a principal quantum number and is represented by the value by the letter n. What is this principal quantum number is telling you is the average distance between the nucleus and the electron. So whether this is electron is the first shell or in the second shell or in the third shell. Okay. It also tells you the size of the entire atom. Okay. And then the energy of the electrons as well. Okay. Usually the energy of the electrons are always higher when they are far away from the nucleus because they are not controlled by the nucleus. When they are very close to the nucleus, they are bound by the nucleus, though they are very low energy. Okay, but they are bound by they are by the nucleus. Okay, and the formula to calculate the principal quantum number is 2n square. So basically, if we have to calculate the number of electrons in each shell, you have to calculate for the first shell. It's 2 into 1 square. When n is equal to 1, it's the first shell. 2 into 1 square, 2 electrons. And 2 into 2 square, it is 4 into 2, 8 electrons. And 2 into 3 square, 9 into 2, 18 electrons. And 2 into 4 square, 32 electrons, and so on. So it tells us that each and every shell, every orbit or shell is the same. So you can have 2 electrons, and you can have 8 electrons, and you can have 18 electrons, and you can have 32 electrons, and you can have 50 electrons, and so on. So that's the first quantum number called as the principal quantum number. It's very important. The second one is called as the azimuthal quantum number. Azimuthal quantum number is also called as the angular momentum quantum number. It is represented by the value, the letter L. Okay. So it tells you the number of subshells inside the orbit. Okay. You have a shell, and then inside each shell, there is a subshell. Okay. There is a model that we sometimes teach about. There is a neighborhood, and then inside neighborhood, there are houses. So that's we call these subshells inside. Okay. And then it tells you the number of subshells, how many subshells are there, and what are the shape of those subshells, and the energies of those subshells. The subshells are named as S, P, D, and F, where F is the higher energy. whereas S is the smaller energy. Okay, because they are farther away from the nucleus, because they are more complicated. Okay? The value of the L will always be n minus 1. Okay, when n takes a value, L will always take n minus 1 value. Okay, so when L is equal to 0, we call that subshell as S. When L is equal to 1, we call this as P. When L is equal to 2, we call this as T. And when L is equal to 3, we call this F. Okay, so this all we know that for the principal quantum number, the first n value is n is equal to 1. N cannot be 0. N starts with 1. 1, 2, 3, 4. But an azimuthal quantum number, since the n value starts with 1, 1 minus 1 will be, first value is going to be starts with 0. Okay. So it starts with 0 as the first number. 0, 1, 2, 3, and so on. S, P, T, F, G, H, and so on. So when you have L is equal to 0, the maximum number of electrons that we can have is 2 into 2L plus 1. So 2 into 0 plus 1 is 1 into 2 is 2 electrons. So S can hold only 2 electrons. P can hold 6 electrons. D can hold 10 electrons. F can hold 14 electrons. If you can see that we have just added only 4 to each one of them. 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. So if you look at this, the formula for this one we saw that was 2n square. Here we are saying the formula is 2 into 2L plus 1. Okay, you have to remember this. But if you just do it for several times, you will automatically know that these values. Okay, so 2, 8, 18, 32, and 50, and 2, 6, 10, and 40. So eventually where we are coming, so in the 1s, you have only, in 1s, you have the first shell, you have only 2 electrons that is possible. That means you have, in the S, you have only 2 electrons that is possible too. Okay. But in the second shell, you have 8 electrons possible. So in the second shell, you will have both an S and also P, which both of them will give 8 electrons. The third one, if you look at that, you will have 2. The third one, you have 18 electrons. So if I add these 3, 2, 6 plus 10, you will get 18. So the third one will have both S, P, and D subshells. So that's how I have, just to make sure that you understand this, I have drawn the first shell. The first orbit is called as the first one. Second one is called as the second orbit, third orbit, fourth orbit. So I have drawn the first orbit has 1s electron, 1s orbital. The second one will have 2s and 2p. The third one will have 3s, 3p, and 3d. The fourth one will have 4s, 4p, 4d, and 4f. Okay. So this is how it is organized. Okay. You should have a clear picture about both these numbers. If you understand the principal azimuthal quantum number, then the rest of them are very easy. Okay. The third one is called as the magnetic quantum number. The magnetic quantum number is going to define a value. The m value is going to have minus L to plus L values, including 0. Let's take if L is equal to 0. S is going to take minus 0 to plus 0, including 0, means only 1 0. So m is going to take only one value. But when L is equal to 1, when L is equal to 0, it is S. When L is equal to 1, it is P. It is a P subshell, right? We saw that. When L is equal to 0, it's S. When L is equal to 1, it's P. But when L is equal to 2, it's P. But P suborbital can have how many subdivisions? How many suborbitals it can have? It can have 3 values. It is like a number line. Minus 1, 0 to plus 1. Okay, minus L to plus L. So it can have minus L, minus 1 to plus 1. So including 0. So it will be minus 1, 0, plus 1. So it has 3 values. So we are going to define as Px, Py, and Pz. That is the reason when I draw here, I draw three boxes here. P's are always written as is in three suborbitals, by which each suborbital holds two electrons. So it will come to exactly 6 electrons. Now, if I have L is equal to 2, D has to take 5 values. It will take -2, -1, 0, +1, and +2. So it is going to have its expands at dxy, yz, zx, x square minus y square, and z square. So you have 5 suborbitals. So when you fill up the electrons, you're going to fill up like this. So all the s orbital are going to have only 2 electrons. Wherever they are, they're going to have 2 electrons. And all the p orbitals are going to have 6 electrons. They're going to fill like this: 1, 2, 3, 4, 5, 6. All the p's are going to have 6. This is not the order in which they are going to exactly go. Okay, I'm just showing for all the p's and all the d's just to make sure that you understand there is 10 electrons. Okay, there's an off order for the electronic configuration that we are going to go later on. Okay. So D's are going to have 10 electrons, and F are going to have 14 electrons. Actually, in the electron, if the off-bow order, the electron is going to go in a different fashion. Okay, first it's going to go 1s, and then followed by 2s, and then to 2p, and then to 3s, and then to 3p, and then to 4s, and then to 3d, and so on. So that's what we are going to look at later on. Okay, so the last and the fourth quantum number is called the spin quantum number, in which the electron spins either upward or downwards. Just to make sure, that's why I wrote the electrons either spinning up or spinning down, like this, up and down. Okay, so these are the 4 quantum numbers that you know. The reason why we are writing these 4 quantum numbers like n, l, m, and s is to tell n, n, l, m, s values, just to specify only which electron we are talking about. Okay, so we can clearly say which electron we are talking about, because all the 4 quantum numbers will not be same for any electron. Okay, so let's look at some examples, then you will understand. Let's take helium. Okay, the electronic configuration of helium is 1s2. So if I have to write n, l, m, s value, the electron, both the electrons are in the first shell. Okay, the n value is going to be the first electron and the second electron. The first electron and the second electron. The first electron is going to be, the n value is going to be 1. Both the electrons are in the first shell. So we are just talking about the first electron and the second electron. Okay, just for reference, 1, 1. And L, when n is equal to, when n is equal to 1, L is going to be n minus 1. Okay, so it's going to be 0. Both of them is going to be 0. When L is equal to 0, M is going to take values -0 to +0, including 0. So there's automatically is obviously 0. But one electron, when it spins up, another one is going to spin down. So it's going to be +½ and -½ So you see that 3 quantum numbers are same, but the fourth one is different. Okay, so that's how, if you write down all the quantum numbers for any element, then you will see that each and every electron will have a different at least one quantum number will be different. This is like an address of an element of an electron. Excuse me. So then you will be able to understand that you can specifically talk about, we are talking about the 10th electron or the 11th electron. Okay. So from this is deciphered from the electronic configuration. Okay. So if you know the electronic configuration, much easier to write down as well. Okay. So the electronic configuration is nothing but the the first number refers to the principal quantum number, and the second letter is going to be is referred as the azimuthal quantum number, and the number in the superscript is nothing but the electrons. So basically, this is nothing but NL over electrons. Right? So we have going to I'm going to show you how to do the off-bar order. I'm going to show you the off-bar order and then write the electronic configuration easy. So when you do that, you can check how to do how to write uh, quantum numbers. But as far as AP is concerned, I have never seen any questions coming in quantum numbers so far, very recent. So, but you should know that these exist, and it's better that you have a very clear picture about this. Okay. Thank you so much.